All right, hello everybody, and welcome to today's webcast. Today we are going to attempt to demystify AI. Just to give you a quick introduction, my name is Amanda Teschko. I'm a principal data and AI consultant at Thorogood. I'm joining us today from our Philadelphia area office, and I'll also be joined today by my colleague Andrew Kennedy, who is also a data and AI consultant with Thorogood, and he's joining us from the other side of the world in Singapore. For those of you who don't know Thorogood, we are an independent global professional services firm that really specializes in data and AI strategies, solutions, and services. We're a global company with offices in London, Boston, Philadelphia, Singapore, Sao Paulo, and Bangalore. And we offer a full range of data and AI strategies, solutions, and services. Our approach at Thorogood is really strongly rooted in ensuring that solutions are delivered in a way that gives careful consideration to the breadth of technical possibilities, but is really strongly guided by business goals and value delivery. We work with a number of large customers, so I've given you a sample of some of them here, and we tend to focus predominantly in the consumer goods, pharmaceutical, and financial services sectors. We're also a technology independent consulting firm, and that we partner with many of the large cloud and technology providers and platforms. And though today's webcast won't really be technology specific, you'll see some demos in things like Databricks and Azure, and we'll also look at leveraging a combination of some proprietary and open source tools. So for the session today, I'm going to start out by trying to demystify AI, talking a little bit about what's happening and how does it work so that we can get a little more comfortable with it. And then I'm going to hand it over to Andrew, who's going to give you a tour of a couple business and practical applications of AI so that you can really kind of pair that with some of the theory and concepts. I'd like to start the session today by looking at this chart that really looks at Google search trend history for the AI search term over the last 5 years. And we can see that at the end of November in 2022, something really happened that drove a lot of mainstream interest in AI. And many of you will probably remember what was happening in that last week of November that sort of brought AI into the mainstream. In that week, the release of ChatGPT really got worldwide coverage as the public got a firsthand glimpse of some of the recent AI advances. We really saw large sums of money being invested in the space. So Microsoft investing a pretty massive $10 billion then into OpenAI back in early January of that year. And then other cloud vendors really racing to release their own language models, creating what's been alluded to as a little bit of an AI arms race. And then what we've really been seeing in the past year is that a lot of reports about the pressure that these advances are really putting on executives, with companies kind of both lured by the opportunity that these tools could present, but also really driven to sort of stave off disruption that could occur if their competitors move more quickly. And during the past year or so, I feel like there's sort of been this feeling amongst many people that what they're seeing when they're engaging with something like ChatGPT was magic, that it was unexplainable, and perhaps that it did sort of come from nowhere, which left people feeling pretty excited, I think, but also a little bit overwhelmed. And so it was really sort of from that kind of chaos, excitement, fear that this session was born. My sense as I was talking to a number of our customers and colleagues and friends was that people were really in need of a bit of a demystification of AI. So a recognition of all that AI is, all the power it has, the potential it holds, but really with a clearer and easier to understand explanation of actually happening. And how can we make sense of it both conceptually and practically so that we can apply it sensibly to our businesses? And so I do hope if you take nothing else from this webcast, that you walk away with a sense that actually it's not magic and it hasn't come from nowhere. Now, one of the people involved in the AI revolution is Andrej Karpathy, and I will reference him a couple of times in this presentation, so I thought I should introduce him to you if you are not familiar with Karpathy. He is an AI researcher, and he was one of the founding members of OpenAI, the company behind ChatGPT. Prior to that, he was the director of AI at Tesla. He really led the computer vision team for Tesla's autopilot, a PhD in computer science from Stanford. He's also a lecturer there and was really responsible for developing one of the first deep learning courses that Stanford offers in its AI curriculum. So this is all just to say that this is a man who is pretty deeply entwined in all things AI. Now, in 2017, which, a number of years ago now, Karpathy wrote a paper that I think was really interesting, where he looks at how classical programming differs from machine learning. And I believe that understanding this shift is really important to make sense of the progress that we're seeing in AI at the moment. So in classical programming, we would start with rules and data as inputs. And we would have to write a program that effectively applies those rules to the data to be able to arrive at answers. Now, in machine learning, this approach happens a little bit differently. So rather than creating programs that require rules and data, we give a machine learning program examples of data and the answers that we would expect or that we have seen, and we allow it to search for the rules that might explain how that data gets converted into answers. In that process, we think about the rules as really being kind of a series of dials that we can tweak in different ways to try to match the answers that we're seeing or that we have. And these dials that I refer to are what you may hear referred to as parameters when we're talking about neural network or machine learning models. And if we have a lot of different parameters or a lot of different dials, we can create more and more complex and nuanced rules that try to explain how that data got to the answers that we saw. Now, in his paper, Karpathy labeled these things software 1.0 and software 2.0. And in the paper, he recognizes that a large portion of the real-world problems that we see actually have the property that it's significantly easier to collect the data rather than to explicitly write a program that writes all the rules into it. And because of this, around that time, what we were seeing was a really massive transition across the industry, where a lot of the 1.0 kind of classical programming code was being ported into this 2.0 code. And while software 1.0 was sort of eating the world at that point, taking over all sorts of things, what we started to see was that software 2.0, or AI, machine learning, was starting to eat software. I think it's really interesting to think about this because when we try to understand a little bit more about what's happening in some of the models that we see today, it's very much this software 2.0 approach that has allowed the way we go about developing AI to evolve in the way that it has. And hopefully this will become a little bit clearer as we break down things a bit more. I think we should start by talking a little bit about ChatGPT. And I will preface this by saying that though ChatGPT really excited the recent surge of interest in AI, I think it's important to note that it's one application that's built on one model in one part of AI. But what it does is it represents a greater movement that's been occurring in the capabilities of AI. And while this represents just a sliver, albeit a very impressive sliver, I do think understanding ChatGPT is a helpful gateway to deepening our understanding of what is happening more widely with these generative models. So that's why I think I like to start there. So let's talk about ChatGPT. Now, you probably know this by now, but ChatGPT is an application, and the application uses a very specific variant of a family of foundation models that are called GPT. And these models are used for natural language processing, or NLP, as we'll commonly hear it called, and they were developed by an AI lab named OpenAI. Now, GPT stands for Generative Pre-trained Transformer, and this family of models is trained on massive amounts of text data. And by family, I really mean that there are many versions. So there was a GPT-2, 3, 3.5, 4, and each version has really advanced the capability of the natural language processing in these models. Now, we'll unpack some of these terms in this presentation. So if you're wondering, what is the foundation model? What do we mean by fine-tuning? We will get to that. But for now, we're going to dissect this kind of particularly scary phrase in the middle. So what do we mean when we say generative pre-trained transformer? Because I think breaking down that phrase helps provide some good context into what's happening within these models. So let's talk about GPT. Now, the generative aspect of this is fairly straightforward. The generative bit refers to the model's ability to create original, coherent, and contextually relevant text that doesn't exist directly in the training data set. And so when I ask ChatGPT something like, write me a limerick about what generative means, it's able to create something that it hasn't been trained on. It hasn't retrieved this poem from something it's seen before. It was able to author it in this sort of creative and generative way that many models of the past weren't quite able to accomplish. Now, there is some debate about what is a generative model and what is not a generative model, particularly as there's pressure, I think, for a lot of organizations to implement generative AI. Now, typically, these generative models are being referred to as any of these models that can create some form of image, text, audio, or sound. But it's really important to understand that the algorithms and approaches behind these generative models can actually be applied to a number of different use cases. And we'll touch on that in a bit. Now, when we talk about the pre-training aspect, this is another really important part of the model. So pre-training for these particular models occurs on a broad corpus of information before it gets fine-tuned on smaller task-specific data sets. And the pre-training really helps learn the general features in the data. Now, these models are trained on very diverse data sets, so things like books, articles, websites, other textual material. And while the architecture and algorithms behind this training might be quite complex, pre-training for these NLP models is effectively just teaching the model to predict the next word. So if I think about trying to predict the next word in the sentence, the best thing about AI is its ability to, there may be some probability that it's any of the words in the list here. And what researchers have found is that if they always took the highest probability word, so the word that's seen the most in the training data, these models would actually tend to go on pretty narrow paths and could get off course pretty quickly. But if we introduce some randomness at this stage, so if we randomly select from some of the highest probability words, that tended to make the models a little bit more creative, but it also tended to steer them towards the right direction. And this is why when you ask ChatGPT the same question twice, for example, you're going to get a slightly different response. It's that randomness that's sort of built in to how the next word is predicted. So a question I've been asked about, how is this pre-training different from just like training a model? What is significant about it? And you can think of pre-training as something that's very valuable when there are some common rules that can be applied widely to a number of different use cases. So for example, the ability to predict the next word in human language, or the ability to detect edges of objects and images. Rather than needing to learn all of these things from scratch every time, pre-trained models really give you a head start because the model has already been trained to understand the basics of that information. And we'll talk a little bit more about this in some of the upcoming slides. Now, the transformer bit might be one of the more complicated or technical parts. A transformer is a newer type of neural network that is very good at processing sequential information, like words in a sentence. So when we're trying to do natural language processing tasks, where it's really vital to hold the context of what's happened earlier in the conversation or earlier in the paragraph or earlier in the sentence, models that can handle sequential information are very important. And these transformer models, it's important to note, came about in 2017. Now, I think it's interesting here just to do a little bit of a quick history lesson to think about how these things have sort of progressed over time. And a lot of our fascination with natural language processing can be dated back to the 50s with the Turing test. So in the Turing test in the 50s, Alan Turing was really interested to think about how could we create a machine whose intelligence could match human intelligence. And the test was that if a human couldn't differentiate between whether they were interacting with a computer or another human, then the system would pass the Turing test. And that's really kicked off a decades-long interest in trying to understand and tackle natural language processing. In the 70s and 80s, we saw a lot more rules-based approaches applied to NLP. So when we think about software 1.0, about this idea about giving a model data and rules and then trying to create programs, this was really how natural language processing was approached in the 70s and 80s. In the 90s, we started to bring in more statistical methods such as Markov models, but it really wasn't until the 2010s where we started to see the greatest progress made in the space, and that was really due to the deep learning revolution. So what do we mean when we talk about the deep learning revolution? That was when we've really seen a shift towards doing more and more software programs using very large neural networks. And if we think about the 2.0 approach, this is where rather than feeding something data and rules, we're feeding these models data and the answers, allowing the model to set a number of different parameters or tweak a number of different dials, as we talked about, to figure out what those rules might be so that they can mimic the data that we're seeing. And this has really brought about a lot of advancement to natural language processing. Now, it wasn't until 2017 I mentioned that the transformer architecture gets released, and that gets us better at processing sequential information. It's really that transformer architecture that allowed the emergence of these foundation models. So models like BERT and GPT, which we'll talk about in a moment, to become released to the world. Models that are heavily pre-trained and allow others to build upon them. And it's only really been in the last few years that we figured out how to scale those models and specialize those models in a way that has allowed us to see the sort of elegance that we're seeing with applications like ChatGPT in the natural language space. So all of this is to say that when we say it seems like magic, but it isn't, that's because we're really just predicting the next word. And when I say it seems like it came out of nowhere, but it hasn't, it's really the progress you're seeing now has been an evolution of a decades-long journey to try to make progress in this space of being able to communicate intelligently with computers. So we've given you a lot on this slide. I want to dig in a little bit to the basics of neural networks. We don't need to understand it in depth, but I think having an understanding of that will help you understand how this next word gets predicted and why the deep learning revolution has really contributed to the progress that we're seeing now. Neural networks can scare a number of people, but I remember the very first time neural networks made sense in my mind. And in that scenario, the person explaining it to me illustrated it as an evolution of a linear regression model. And so I thought I'll try that approach with you to see if this helps. So in this very, very simple example of linear regression, let's assume that we have some data to plot that illustrates the relationship between temperature and ice cream sales. Now, in this simple linear regression, our temperature is our X values, or our inputs, and our sales, or our Y values, are our outputs. And the way we would typically do regression is we'll try to draw a line that represents that relationship that we're seeing between those two things. Now, you may remember from your maths classes, or maybe you don't, but a line can be represented by the formula of y equals mx plus c, or b, depending on which part of the world you learned it in, where m is the slope and c is the intercept. So in this case, we would say that to model our sales, we would multiply temperature by 2 and add 1. So let's start to put this in the form of a neural network. Now, the simplest neural network has an input layer and an output layer. And between the input and output layer, we multiply the slope and add the intercept. So this should look fairly recognizable to you. You may remember that we can do multivariate regression as well. So we can start to add more variables in. So instead of just looking at temperature, maybe we look at day of week and month of year. And we might have specific slopes that apply to each of those as well that effectively get applied to the inputs to get to our output figure. So how does this evolve to become a neural network? Because right now we're just kind of fitting lines to dots. In a simple neural network, we still have an input layer and we have an output layer where we can think about, in this case, 3 input attributes such as temperature, day of week, and day of month. And at the end, we expect to have 1 output value, the ice cream sales for each record. Now, where neural networks differ is that they also have hidden layers, which give the model more degrees of freedom to be able to model more complex relationships between the inputs and the outputs. And these hidden layers are made up of nodes. So each kind of yellow circle here is a node, and the vertical stacks are referred to as layers. We often refer to the number of nodes and hidden layers as the neural network's architecture. And this simple neural network has 2 hidden layers of 2 nodes each. Now, each node in the input layer connects to each node in the first hidden layer. And instead of multiplying this input by a slope like we did in regression, in neural networks, we multiply each input by a weight. Similar to regression, we also add something akin to an intercept term, but in neural networks, we call this the bias term. Now, each node in the hidden layer is calculated by taking an input node and multiplying it by a weight, and then adding the bias to it. So when you hear people talk about weights and biases in neural networks, this is what they're referring to. These layers get connected together. So the first layer then becomes the input for the next hidden layer, and applying weights and biases. And the output of this layer then gets passed to the final output layer with more weights and biases. And we can think about the weights and biases as the parameters in the model or the dials that we were talking about earlier. And in order to fit this model, we just basically iteratively adjust each of these parameters to try to recreate the rules that map the inputs to the outputs that we have seen in the past. And we can liken this back to software 2.0. Now, it's important to note that this is a bit of a simplification. There's something called activation layers, which apply to be able to model nonlinearity, for example. But that's a level of detail that we won't go into today and isn't really necessary just to get kind of a conceptual understanding of how neural networks work. So something that is interesting to note in this model is that we've got about 18 parameters. So if we add up all of our weights and biases, this is a very, very small neural network. And the neural networks that are fueling some of the models that we're using today are massive. Many more hidden layers, many more nodes. The most extreme example is probably one of the latest versions of GPT, GPT-4, which has 170 trillion of these parameters. So that starts to give you a sense of how complex these models can be and how complex the rules can be to be able to predict the next word. Now, when we take these very large neural networks, adapted by the transformer architectures that we talked about, so that we have a better understanding of context within the sentences, and we do a lot of pre-training, we really get the ability to create what we're calling foundation models. Now, foundation models are large models. You can think about GPT, BERT, Stable Diffusion are a couple examples of this, and they're capable of performing a wide variety of general tasks, particularly in the language and image space. And the idea with these models is that they can be used as a starting point for AI developers to refine and create new, more specialized applications and models more quickly. It essentially gives you a base model that already has a good understanding of some of these things, how to detect images, how to understand language. And then you can build upon and evolve those models. Something that's interesting to note is that foundation models are kind of called out and defined in the EU AI Act, which in many ways I think we're expecting to kind of be the first real formal regulation in AI. That's because foundation models can be very beneficial for companies, but because they can be adapted to so many different tasks, they can be quite prevalent in the space. So they could be used in many, many downstream applications. And so if there are any underlying biases, or if there's anything running amok within these models, it creates greater risk because it has the ability to permeate into many models that have been built on top of them. And so because of this, the EU AI Act is identifying foundation models as something that come with higher levels of risk and that have to be regulated to a larger degree than maybe a model that has just been built for one use case by one company because of how pervasive they can be and how widely they can be used. Now, these foundation models are really fascinating, but they're not that useful by themselves. They are really much more valuable when you start to customize them with your own data and for your own use cases. So they're meant to sort of be specialized. And you can think of ChatGPT essentially as a fine-tuned version of the GPT model that we've been talking about that has really been optimized or specialized for conversation. Now, these models can be customized in two different ways, or two kind of types of ways, either through fine-tuning or through prompt engineering. And I won't cover these in a ton of detail today, but you can think about fine-tuning as training these models on more information so that the parameter, all those 170 trillion dials, get adjusted and updated to learn your data. Now, you can imagine that doing this requires running many new training examples through the data, and it also could be quite computationally intensive and expensive. So there are some techniques that can kind of minimize this, like parameter efficient fine-tuning, for example. Fine-tuning tends to be a heavier lift to be able to get these models to perform on your data. A lighter touch approach is through prompt engineering. And in prompt engineering, we keep all of the parameters the same, so we don't touch any of the dials that say GPT set. But when we're sending a prompt, like a question to an application, we want to prepend that with context before we ask the question. And we might use different search techniques to kind of find the right context to pass before the question gets asked. Now, we can think about this of if you're trying to find information that exists in a series of documents that you have, perhaps you use a search algorithm to limit it to the most relevant documents, and then the text of those documents gets sent to the prompt before you actually ask the question. And this is one approach that can be used in this kind of prompt engineering technique, but there are a number of different options like few-shot learning, retrieval augmented generation, and you'll see some examples of this prompt engineering today. Now, both of these things are viable, but you would probably want to select the correct approach, really based on the use case, the type of information that you have, and the computational capacity that you have. I do think it's important to note at this point that though these large language models are very fascinating, we do have to really consider how we use them. So going back to Andrei Karpathy, he spoke at a conference, I guess about 8 months ago now, in May of 2023 at the Microsoft Build Conference. And I think it's a really interesting talk. So I would say if you're looking for some content in this space, he does a really nice presentation here. In this presentation, he gives an update on the state of GPT. And he talks about some of the challenges that these models have, that they can fabricate, they can hallucinate, they may have reasoning errors, there are knowledge cutoffs, for example. And throughout the course of the presentation, he really ends it with some recommendations for how they should be used. And his recommendations or guidance for use are that they should be used in low-stakes applications, combined with human oversight, as a source of inspiration or suggestions, and really more as co-pilots over autonomous agents. And so I think it's important to kind of think about some of that guidance when you think about what are the best use cases to start to trial some of these models within your organization. We've talked about language models a lot, but I think it's also important to recognize that language models are just one part of recent advances. And things like advancements in deep learning, neural networks and transformers, pre-trained models, all of these things are really rising the tide for all of the AI and ML capabilities that exist in the world. So AI and language models are not synonymous. AI is actually a broad category that covers a number of different subclasses. And some of those most common subclasses are machine learning, natural language processing, which we talked a lot about today, but also computer vision, robotics, speech recognition. And when I try to think about AI, I think about it as this sort of umbrella that allows us to recreate human capability, where machine learning is really the brain that powers all of it. So we can't speak without our brains communicating with our lips. We can't hear without our brains communicating with our ears. And so it's important to recognize here that AI is this very large umbrella. And if you're thinking narrowly about it as it just being text or image and the applications related to some of these generative models, you may find that that's a bit limiting. There's so much that's happening in the space that can elevate the work that's being done across all of these areas. So I think it's just helpful to think a little bit more broadly about it and to recognize that machine learning is really core to all of these things. It's really the brain behind any of the models and adaptations. And there are many, many advancements in this space that companies should be considering that are helping all of these things just become more sophisticated right now. So a narrow focus on the generative models might leave you missing some of the amazing advancements that are happening in some of the more traditionally machine learning spaces as well. And the last thing I'll leave you with before handing you over to Andrew is, why are these advances happening now? We know that digital transformation created an abundance of information to be consumed, and cloud technologies have really made storing and processing that data cheaper and easier than ever before. We've also seen hardware advances, particularly the graphics processing units and tensor processing units, and that's made scaling up those transformer models that we talked about earlier actually possible. We also know that the open source technologies and communities have really played a very critical role in advancing AI developments, such as the progression of neural networks that we talked about, the evolution of transformers, the development of foundation models. And so that's been a really strong force in making some of these things available today. So with that, I'm going to hand it over to Andrew now, and he's going to talk you through some of the more practical applications so you can get a sense of what some of these things look like in real life.
Thanks, Amanda. So we're going to take a look now at a couple of industry example business cases that will give you an idea of some of the different ways that you can apply some of the models that Amanda's been talking about. In particular, we're going to look at two cases here. The first, making your content searchable. And then the second, we're going to look at using some of the language models for product attribution in a slightly more specific use case there. So the first is about making your content more searchable, making a chatbot interact with it. We dive into that. Many of the customers that we've been talking to have been asking us in various different ways, how can I get better insights from the unstructured data that I have? And so to demonstrate the ability to do that, we took our webcast recordings as our unstructured data set. We've got a huge back catalog of informational videos on data, technology, business. And the question that we wanted to ask was, how can we make the information in these videos easier to dig through. And videos here as one example of unstructured data, a format where there's a lot of information stored in the video. To go and get that, you might have to go into several videos, dig around, get the content, watch different clips. But you can imagine it's not just video. There's plenty of cases that we've been talking to customers about doing this with documents. So that could be various market research documents, or in some cases we're talking to companies looking at contracts and understanding their contracts better. So different ways that you can use this kind of approach. But for here, we're going to show it on videos. And in doing that, we're going to start with a collection of video files. Obviously, for all of our webcasts, we have the original video files. Those go back several years. We're going to put those video files into cloud storage. From there, we'll extract the transcripts out of the video files, store those, and then take those transcripts and we want to put those in a searchable index. And from there, we could either build out a search interface that runs on top of the search index, and actually in a lot of cases, that will already give you a lot of value just being able to search on the data. But there's a lot of interest as well in using chat interfaces and being able to directly ask a question and get a suggested answer to that question based on the content. So in this case, our webcasts. Now to do that, we're going to combine multiple different AI tools together. So Amanda mentioned some of the different areas that are being innovated in AI at the minute. We're going to pick up on 3 in this example. So the first is Azure AI Video Indexer, and that's what we're going to use to get the transcripts out of the videos. We're then going to use Azure AI Search to build the search index. And for the chat interface, we're using Azure OpenAI. Now you can see I'm taking these all from the Microsoft Azure platform. There are a couple of reasons for that. One is that these tools are really visual. They have visual interfaces that allow us to see what's going on with the AI a little bit better than some of their competitors. And in the case of Azure OpenAI, everyone's obviously interested at the minute in ChatGPT, and that's kind of kicked off some of the excitement in this area. And through Azure OpenAI, we can use some of the same models that Amanda was talking about earlier, and the specific models. But it's worth noting, while I'm using examples from Azure, you could equally use other cloud platforms or other tools and combine them in different combinations depending on what your requirements are. The other thing I'll highlight quickly is that we're, alongside those AI tools, we're using other tools that are already in our cloud platform to automate the process and build out interfaces that users can interact with. So we're bringing new AI tools into an already existing data platform here. So with that, I'll dive into the web interfaces and start to show you some of what we're getting from these tools in terms of the AI. So first off, on the screen, you can see Azure AI Video Indexer. And this is what we're using to get various bits of information out of the videos, in this case, transcripts. But here we have some of the webcast videos that we have. You can see here there's an upload button. I could upload them through the interface, but actually for these, we've uploaded them programmatically so that we could take all of our webcasts. As new webcasts come in, we can automate the process of loading them in and handle a lot of videos in parallel. If we go into one of the videos here, I'll show you on the right-hand side here, it's showing you some of the insights that we can get from that video. And this is all automatically extracted by the AI within the tool. So we're able to see things like Raghav, who's presented this webcast, some of the topics that he's talking about. So this is a video on ML ops and moving ML from experimentation to production. So the topics coming up are the ones you'd expect, things like data science, predictive analytics, technology, business, and so on. It's also pulling out some keywords. So if the topics is coming from a fixed list of categorizable topics, the keywords is picking out what are some of the phrases that are repeatedly used in the video. We've then got a set of labels, picking out some of the things that it sees in the video. And then the last one, emotions. For our webcasts are very focused on information and providing useful knowledge. You can use educational content. So maybe the emotion isn't as high as it would be in some cases, but we've seen scenarios where customers are looking to analyze say advertising content where the emotion might be slightly higher, or we've looked at podcast content in the past, and you'll see a whole range of emotions coming through. So it depends on the content, and in some cases, different sets of insights will be useful in different business scenarios. What we need here, though, if I switch to the timeline, is the transcript. And you can see on the screen there, it's pulled out the transcript, so it's taken the audio from the video and put that through speech recognition AI to give us the different things that are being said. And we can extract that information and save that back into cloud storage automatically using that programmatic approach that we talked about. And we'll do it not just for this video, but for every video in this set. And so from that, we could build up a search index that will allow us to either search, or as I said earlier, we can chat and ask questions of the video. And that's what we have here. We have an interface that allows us to hook into one of these large language models that Amanda was talking about. And if I type in a question here, I start with what is MLOps? Once I type in that question, it's going away, it's running that search, searching for the relevant video content, looking through the transcripts, and it's put together a description here of what is MLOps based on all the information that's available to it from the videos. Really, a really important thing for a lot of the customers that we're talking to, looking to implement this kind of thing, it's calling out the references here. If I click on this references button at the bottom, you can see these little numbers refer to specific videos that the contents come from. Actually, here is the one that I showed you on the screen earlier. So it's found that as a relevant video, and it's showing me the parts of the transcript that are relevant. Actually, if I really wanted, I could go back, click on it, and it will take me to the original video on the Thorogood website. If I wanted, I could type in another question, and it will go away and generate the answer to the follow-up question. In this case, it's looking for slightly more context. It usually picks up the topic, but in some cases, you'll need to remind it exactly what you're looking for. But it will always answer, or always try to answer in the context of videos. And if it can't find that information, it should tell you there isn't information on that in the transcripts available. So just stepping back into this, the set of technologies that we're using, now that we've seen how it works, I'll just call out again a couple of the key points. So here we're using multiple AI tools together to achieve the solution that we want. The first AI video indexer, in this case, actually we're using it for audio transcription. We're using one AI tool there. The second one, AI powered search. And so although I've typed in what is MLOps, it's not just looking for those keywords. If there are other related words, it'll pick those up. And for the large language model, we're using Azure OpenAI. So we're combining here the different tools that we need, different AI tools provided by the platform, into one overall solution. And that very often is the sort of thing that we'll do when we're building up these kind of AI applications. Second thing to note, like I said, we built this on Azure. You could switch in. There are tools from Amazon and AWS. There are tools from Google that do very similar things, and there are tools from other providers as well. And those are some that we'll use in the second use case. In this case, we're going to look at using large language models for product attribution. So this is a scenario that we came across with a customer that we've been working with for a very long time. We're working with them on a project where the key objective is to strengthen the relationship between this customer as a consumer goods manufacturer, trying to strengthen the relationship between them and their retailers. By using shopper data, we've been able to identify shopper purchase patterns, which have helped the retailers to place the right set of products onto the shelf and improving the business in a manner that's beneficial for both the manufacturer and the retailer. And it was in one of the conversations with that customer that we understood they wanted to analyze the performance of natural products in the market. There's a belief that natural products is a particular growth category, or has been for the last couple of years. Now, one challenge in looking at the natural category is that they don't have the natural attribute directly in their data. And they tried creating that manually based on the description, but there are a few reasons that we'll get into that doesn't work so well. But what we looked to do was to see, can we do that using some of these large language models? And that's what we wanted to explore in this scenario. So as a bit of background, the place that we're going to start is we have product descriptions. In this case, I'm showing a product description from a retailer website. And if we look at this, we want to use this product description to classify the product as natural or artificial. And if I highlight some of the key phrases that we might pick up on in the description here, apple cider vinegar, oat is the first ingredient, free from sulfates, parabens, and dyes, we might start to see some of the places that you could pick up that this might be more of a natural product. But if we look at a set of product descriptions side by side, you'll start to realize that different products are described in different ways, and there isn't one clear set of rules to define a natural product versus an artificial product. And the other challenge is, if you try to do this manually, go through all the products, it gets prohibitive pretty quickly. It's very hard to keep a consistent set of definitions. And the more of these you go through, the more you start, you know what it's like for a human going through this kind of data set. You start looking for shortcuts and trying to kind of invent your own rules. And so we wanted a way to do this automatically using some of these models that aren't going to tire or get bored, and that could do it more consistently across the data set. So the goal then, starting from those product descriptions, and they can be very varied, our goal is to attribute the products as natural or artificial, and then once we have a way to automatically get that tagging, we want to make that available in the data set for further analysis, just like you would with any other tagging or attribution that you have for your products. And to do that, we're using open source pre-trained large language models. And I'll touch in a second on what some of those are. But we're going to take three different approaches, and this goes back to some of the approaches that Amanda talked about earlier. The first, zero-shot learning, and that's where we're going to give it the product description and ask the model to classify it as natural or artificial just based on that product description. So in that case, the model has no knowledge of our data or domain. We're not really giving it any context, but in some scenarios, it works well. So we'll see what it does on this data set. The second example, few-shot learning, is where we give the model a few examples to kind of prompt it into how it should, the sorts of phrases it should be picking up on for natural versus artificial. And in this case, it allows the model to have some knowledge of our problem and domain and the sorts of words that it could be looking for. The third scenario is one where we go in more detail and do proper fine-tuning of the model. This is a more intensive process where we update the parameters of the model using labeled data. And since those parameters are updated, it allows the model to be fine-tuned to the specific data set and the domain. And so in some scenarios, we'll expect that to perform better than some of the other methods. In what I'm demoing, we're going to use three different models, one for each of those approaches. So there are different models suited to each of the approaches that there are. So the three model creators shown on the left-hand side of the screen. And then on the right, I'll show you quickly Hugging Face, which is where we can go to get some of these models. Databricks, where we've written and where we run a lot of the code, and then Databricks is running on the AWS platform. You won't see that as much. It's not too obvious I'm running on AWS, but just so you know where it's happening, that's where the compute is. We'll take a look at the other tools as we go through. So let's dive into browser again and take a look. I said I'll show you Hugging Face, and this is where we'll go to get some of our models. So we go into Hugging Face. Hugging Face really has emerged as a community hub for model creators, people who are looking to find the models that they want to use. There are various different things you can do in Hugging Face. There are data sets, there are code tools in it. I'm going to go to the models page because that's what we're interested in here. You can see there's 530,000 models or thereabouts available to us. Thankfully, there are some filters that will help us on the left-hand side. For example, for some of these language models, if you know there's specific languages that you want to use, particularly in the translation case, that's pretty useful. But you can also do it more generally, look for the languages. If there's specific licenses you want as an organization, so if you need it to be a license that you can use for commercial use, you can check off the license types that you're happy with. One of the really important ones, though, is tasks. And I've said we're going to start with zero-shot classification. So let me click here and filter down to the zero-shot classification models. Now, by default, it's sorting by trending. I can sort it in various different ways. Most likes, if you want people who have liked something. Most downloads is also quite often used as an indicator of the fact if a lot of people have downloaded it, probably there's a lot of people using it. It's been thoroughly tested. So if I click on that, we've got this Facebook BART large MNLI that comes up at the top. If I click on that, it will take us to a model card. This is giving us a lot of information about the model, which in general is very useful for responsible AI, model transparency and understanding how the model is trained and how it works. It also has some code examples that you can use, various things that you could refer to in here. I'm going to use this model because it's the top of the list. I'll use that one just to try it out first. And so we'll switch into Databricks. And this is where I would start writing the code. Now, don't worry, I'm not going to get deep into the code here. If you're looking at the screen and thinking, we're going to do a lot of coding here, don't worry, I'll show you some of the key bits, but mostly I want to show you the outputs of it actually. So the first thing we're doing is loading the data set in. So we're loading in a set of product descriptions. And actually to get this started off and to be able to test it, we have got some that have been manually labeled. So we've done that here for a subset of the products. So there might be thousands of products in the market that we're interested to categorize. We haven't tagged them all. We've tagged a significant subset of that so that we could do the testing and see how well the model's performing by comparing the automatic outputs, the AI model outputs to the manual tagging. And that's where we'll see some accuracy percentages later. Then in the zero-shot learning, we're specifying the candidate labels. So that's natural and artificial. That's the one thing we give it. We're going to use this one line of code to connect to Hugging Face and get that Facebook BART large MNLI model. If I wanted to change the model, you can change it in this line of code. And then we're going to pass in this prompt. The prompt in this case is just the product description. And we've set this up to automatically run across all of the products in the data set, all of the labeled products in the data set so that we can calculate the accuracy. And for this zero shot scenario, you can see it's giving us 25% accuracy, which isn't high enough at all. Different scenarios, different levels of accuracy might be useful, but 25% actually is worse than random choice. So we need to do something slightly better than this. So that's where we come to taking a look at few-shot learning. And in few-shot learning, like I said, we give it some of those examples. So here in our prompt, we give it an instruction to start with, but then the description. So description of a product that's categorized as natural, then one later that's categorized as artificial. And from this, it can start to pick up some of the kind of the trigger words or an idea, or at least get a sense of the different range of products that we're including here. And so finally, then we pass in our new product description and ask for a category. And when we run that over several products, it's up to the bit. We've got to 38% this time, starting to get slightly higher, but we still need to get better than that before we can start to use it in this scenario. We wanted to get something better, and so we applied fine tuning. So in this case, it's actually going to take some of those labels that we've applied and use that to customize the parameters a bit. So we've got a training data set and a test data set, and we're going to get the accuracy based on that test data set. This takes a bit longer, but once it's got that information here, you can see in this scenario, by using this approach, we've really got our accuracy much higher. Now, all of these accuracies are going to be very dependent on the use case, the quality of the data that's there as an input, the types of outputs you're looking for, all sorts of different things. And it depends on the use case as well, what level of accuracy is going to be useful for you. In this case, 88% is giving us a lot more information than having no categorization, and it will allow us to start taking a look at the different product categories compared to each other. And that's where, if we automate this process, we could start to build this into our standard dashboards. And here, give an example of what it looks like for a customer when we bring just the natural and artificial side by side. You can start to look at how those trends compare to each other, or you can use it as filters, slice and dice the data in whatever way that you would, and just use that natural and artificial labeling as you would any other attribute in your data set. So from that, just to round this out, we set that goal, attribution is natural or artificial, and we've shown that we can use these models to do that, and then make it available for analysis. So once we've created that attribute, save it back into the data set and use it as any other standard product attribute from a structured data source. Use it to slice, dice, filter, get a sense of how the different categories are performing, or analyze our products in whatever way we want to. And based on that, we can make recommendations to the retailer as well as the manufacturer and find ways for them to collaborate and make the most of the trends that we're seeing in this new and emerging category. So that rounds out the two business cases that I wanted to show. So just to quickly round up with a few potential next steps. And really, I'd say that the key thing on next steps is, talk to us, let us know what of this is of interest to you. There are other topics that we've used coming off the back of this. The first I mentioned in the first business case we showed about, we've done it here for videos, but there's scenarios that we can do that for market analysis documents or other sets of documents that customers have. So if you want to talk to us about the different sets of documents that you're interested in, or the different content that you think you could get information from. The second thing is we're talking to a number of customers about their AI strategy and how AI fits in the wider data and AI strategy in particular, and some of the topics that they can approach as part of that. And if that's of interest to you, I'd suggest reach out. We can have a conversation and take you through some of the thinking that we've been doing with different organizations in the area of data and AI strategies. And as part of that, one of the big questions is how you identify impactful business cases. And we have an approach to doing this that starts from the business objectives and works towards then identifying the AI approaches that will help to address some of the business objectives that you have. And then often we find that leads towards setting up, when it comes to a specific solution area, setting up a series of steps that we can take towards building out the solution. So it starts with smaller steps that are, in one sense, more achievable, but also allow you to deliver return on investment quicker. And we've helped a number of our clients looking into AI and establishing how we could do that in steps and really make that achievable in that way. So with that, thank you for joining us. If any of those topics are of interest, or if you want to talk to us about the wider area of AI, I encourage you, please do reach out to Amanda or me, and we'll be very happy to pick these topics up. But thank you for joining today's session, and have a good rest of your day.